As we look to expand our understanding of matter, let's review our model so far. Our observations are in line with a early ancient Greek philosopher named Democritus. Through his observations and ideas, he postulated that matter is composed of atoms which move through empty space. We were able to observe this with the popcorn activity, where we saw the popcorn smell particles move across our classroom. Democritus also believed that atoms are solid, homogeneous, meaning the same throughout, indestructible, and that they can't be divided into anything smaller. When we do our particle diagrams, we draw atoms as these small, solid particles that are all the same color, and we've yet to try to destroy or divide our particles. Democritus also believed that different kinds of atoms have different sizes and shapes. Again, when we look at two different substances such as iron and sulfur, we designate these different substances with either different colors or different shaped particles. And lastly, Democritus believed that the size, shape, and movement of atoms determines the properties of the matter. Again, we've seen that iron and sulfur have very different physical as well as chemical properties, which could be attributed to their different size and shape. Democritus's ideas were much ahead of his time and unfortunately were met with criticism from other philosophers. The main reason they criticized his work is that he couldn't answer the question, what holds atoms together? There was another influential Greek philosopher at the time, Aristotle, and he strongly disagreed with Democritus's ideas, especially the fact that matter can move through empty space. He disagreed with this because he believed that empty space cannot exist. And then from his observations of matter and nature, he felt anything was made of earth, fire, air, and water. Because he was so influential, Democritus's ideas were completely rejected, and Aristotle's ideas went unchallenged for approximately 2,000 years. It was at that time that scientists such as Joseph Priestley and Antoine Lavoisier carried out experiments that allowed us to confirm some of Democritus's ideas as well as deny or go against what he had postulated. At this time, I would like you to pause the micro lecture, and if you go to the files section of our course, there is a file called Dalton's Playhouse, and you're going to use that file as well as this website to replicate some of the early experiments carried out by Priestley and Lavoisier that will help us to understand Dalton's theory about matter. When you've completed the activity, you'll return to this micro lecture. Now that you've had a chance to observe some of the early contributions to our model of matter through Dalton's Playhouse, we're going to look at how all that information was synthesized into Dalton's atomic theory. He agreed with Democritus in that all matter is composed of atoms, and that atoms cannot be divided into anything smaller, and they are indestructible. He also agreed with Democritus's point that all atoms of the same element are identical. He believed that atoms of one element are different from atoms of another element, or in other words, we can identify an element based on its atom. When putting two substances together, he found that compounds were formed in simple whole number ratios, or more specifically, we'd never have a fraction of an atom or a decimal point of an atom combining with another. And lastly, with each of the chemical reactions carried out by Priestley, Lavoisier, and Dalton, they found that the atoms were not created or destroyed, but just were rearranged to form new substances, which is in line with our observations of the law of conservation of mass. Based on his work, we have a basic definition of the atom as the smallest particle of an element that retains the properties of that element. Once scientists were convinced of the existence of atoms, they had questions about what, if anything else, was inside. The first person to explore this idea was J.J. Thomson, and he looked at the connection between matter and electric charge. I would like you to pause the micro lecture at this point, go to the pages section of our course, and there is a page for J.J. Thomson's cathode ray experiment. There's a short 2-minute video if you could view that, and then come back to the micro lecture as we discuss his work. As you saw in the video, J.J. Thomson used a cathode ray tube which had a ray of particles going from one end to the other, and normally that ray goes in a straight path. But he found when he put an electric field outside the tube that the ray would bend towards or be attracted towards the positive plate. He concluded from this observation that the ray must have a negative electric charge. From his observations and his data, he mathematically calculated the charge to mass ratio of the particle and found that the mass of an electron is less than the mass of the lightest known element, namely hydrogen. In discovering this, he identified the first subatomic particle inside the atom, which was the electron. This disproved one of Dalton's points that the atom is indivisible or can't be divided into anything smaller. J.J. Thomson received the Nobel Prize in 1906 for his work with the electron. With this discovery, he came up with a new model of the atom called the plum pudding model. He knew that the electrons were negative, but matter itself is not attracted to anything, so it must be neutral. So he hypothesized that the atom was a uniformly positive sphere in the background with these negative electrons kind of scattered or embedded throughout. So it was compared to plum pudding with raisins scattered throughout. And this was his new model of the atom. Taking it one step forward, in 1911, Ernest Rutherford started studying how these positively charged particles would interact with solid matter. Again, I would like you to pause the micro lecture and return to the pages section of our course in Schoology. There is a page for Rutherford's gold foil experiment, and there is a animation that I would like you to view, and then return to the lecture. As you saw from the animation, Ernest Rutherford projected alpha particles at a thin piece of gold foil, and he expected, based on the plum pudding model, that the alpha particles would pass straight through. The majority of the particles did, but every so often a particle either deflected at a large angle or bounced straight back at him. Based on his observations, he believed that the plum pudding model was incorrect because it couldn't explain what he was seeing. So he repurposed the model of the atom into the nuclear model, and his explanation was that the atom is mostly empty space in which the electrons are, and that all of the positive charge and mass are condensed in the center of the atom, namely the nucleus. So it was when the alpha particles hit the nucleus of the gold atoms that they would either deflect or bounce straight back at him. This allowed us to complete a new model of the atom, in that we have inside subatomic particles, we have the electron with a negative charge, and in the space surrounding the nucleus, a proton with a positive charge, which is in the nucleus. And then in 1932, James Chadwick discovered the neutron, which has a neutral charge and is also located in the nucleus. You can see from the relative mass that the majority, if not all of the mass of the atom comes from the proton and the neutron. In our next micro lecture, we will look more specifically at how to tell different atoms apart.